So we're doing this new process called field-assisted ion exchange, and what it is, it's a process similar to it's a glass strengthening process that's similar to how they make Gorilla Glass. And what happens is we take potassium nitrate salt and we move it inside the glass and replace sodium ions that are inside the glass, and the end result is that you get a compressive region in the glass. And that compressive stress strengthens the glass, and so it doesn't break at lower tensile stresses. So for our experiment, what we wanted to test is what is the effect of having both sides of the glass strengthened. And so this is our experimental setup, where we place several tubes, there's actually 5 of them, in parallel, and we put molten potassium nitrate on either side, and then we run a high voltage DC current, or voltage across either side of the glass. And what that does is it forces those ions in and strengthens the glass. So if we move down here, what we can see is that when we want to do both sides, we can just reverse the voltage. And so by reversing the voltage, we go one way for double the amount of time, and then we reverse that voltage and go for one amount of a certain time, and we should end up with a compressive stress that looks something like this, where both sides of the glass have equal amounts of strengthening on the inside and the outside. To confirm that we actually, made the glass stronger and that ions actually exchange, we can look at the current. And so what we do is look for ionic conduction. And ionic conduction has a trend in its current over time plots that it's an exponential decay. And so we mapped our current over time for our experiments, and we saw that exact trend. And so we can safely say that ionic conduction is happening. If ionic conduction is happening, ions have to be exchanging, and therefore potassium has to be going into the glass to strengthen it. To characterize what we did, we used a flexural strength test, and we used it on glass tubes. So while it's not very common, what we can do is we can break down what goes on in the stress distribution. So right here we have the upper part of the tube in compression and the lower part in tension, with the highest forces occurring on the edges of the tube. So after we did these tests, what we saw is that for a control, this is the fracture pattern you get. When you break glass, when you strengthen it and you break it at higher stresses, the fragment sizes get smaller, and therefore when they break, like in an explosion, if a glass or something explodes and shoots glass fragments over the top, the smaller the particle, the better, because it carries less momentum. And so if we look at the flexural strength change, when we strengthened, if this is the flexural strength of the control, we strengthen the outside first, and then the inside, we see that there's a 20.65% increase in strength. But when we do the inside first, as opposed to the outside first, we see there's a 125.66% increase in strength. And so what we can conclude from that is that it's a non-linear rate in strengthening. So you're actually weakening one side of the first side of the glass you strengthen. When you reverse the polarity, you weaken that glass. And so because the highest stresses occur on the outside of the tube, what happens is that when you flex it, after strengthening on the outside first, you weaken it, and it basically becomes weaker on the outside as opposed to the inside, and so it breaks at lower stresses. And so that's essentially what we found, is that the rate is critical, or the order you strengthen the glass is critical. I'm ready now. And so for future work, what we'd like to do is do more 4-point bend tests to improve our statistical reliability. We'd also like to characterize how far the potassium went in compositionally by looking at using secondary ion mass spectroscopy, so we can have a compositional map of our tube. And then we'd also like to use burst tests to understand exactly what the strength of the inside of the tube is really like. And so this was only for one type of glass also, so we also would like to extend that to more common types of glasses, such as soda-lime glasses and luminosilicate glasses, which is what Corning uses in their Gorilla Glass. So hopefully we can build a better, stronger glass for the future.